Welcome to our lectures of advanced power electronics and control. Now, we have already discussed actually thyristors and we have discussed basically SCR. Thereafter, we shall discuss actually briefly other member of this family. So, GTO, IGCT, MCT and other, these are the main three members are very frequently used in the thyristor family. Apart from that, static induction thyristor and optically triggered thyristors and bidirectional thyristors also we will try to give a brief descriptions, but most of the application is applied to these three segment SCR, GTO, IGCT and sometime MCT. So, we shall today discuss one of the very important member of the thyristors, that is actually gate turn off thyristors or GTO. GTO is actually gate turn on thyristor. So, it is essentially a thyristors which has a capability to turn off by gate. This is the basic difference of it. So, like thyristor, GTO is a current control device, current control minority carrier, that being a bipolar device. Same thing, it is combination of two PN junction diode, and we think of will come with the structure little later. GTO differs from the conventional thyristor in that they are designed to turn off when a negative gate current sent to the gate. That means we have actually discussed briefly the two transistor analogy in case of the thyristors. When thyristors are conducting, we believe that both these actually transistors are in a saturation region. But then again we have to bring it one of the thyristors in a cut-off region to turn it off, and subsequently other thyristor will turn off. A relatively high gate current is needed to turn off because there is a trap charges in that P2 region, and typical turn off gain in the range of actually 4 to 5. So, we require larger negative current to turn it off. Let us say if you are turning off 10 ampere current through the GTO, you require a minus 2 ampere of current, something like this kind of values will come. So, huge negative current you require to sink to operate a GTO. During conduction, on the other hand, device behaves like a thyristors and with very low on state voltage drop. This is one of the advantage where other device will find, like in case of the IGBT and all those things. So, this is a symbol of it, and we can draw any of it actually. So, bidirectional gate current can be shown like this. Ultimately, interdigitized gate cathode structure actually increases the DIDT rating of the device, also improve turn off performance of the device. So, essentially you have this is anode, this is actually junction J1, same as that actually thyristor. Thereafter you have a buffer layer, thereafter actually you got a N junction, thereafter P junction. So, this buffer layer is there to actually sustain high forward and a blocking voltage. So, thereafter you got a P junction and followed by gate and cathode. So, you can see one thing that this is the junction J2 and this is the junction J3. Buffer structures is there to increase the high blocking potential in reverse as well as the forward direction. And in this case, anode shortest structure to decrease reverse voltage blocking capability. So, this is basically little difference from the conventional thyristor. How does it work? We have to go back again the two transistor analysis. Basic operation of the GTO is same of the thyristors, Principal difference lies the modification of the thyristor structures which have been discussed in the previous slide. To achieve the gate turn off capability, it will have large alpha 2. So, alpha 2 corresponds to this NPN transistors and it will have large alpha 2, and you know that to make it in a conduction mode, then in a model alpha 1 plus alpha 2 should be equal to 0. So, alpha 1 plus alpha 2 is just little larger than the critical value of 1. Short distance from the gate to cathode makes it possible to drive the current from the gate. So, this is upper one is the NPN transistors and you can turn it on, and so it will have a first turn on, and thereafter what happens, thereafter you can off it, but then you have to change the signal and change the alpha 2, and you have to make transistors inside the structure, inside this GTO into the cut-off region, then you can achieve this turn off of this device. So, essentially when turns on, then equation become this IC1 equal to alpha p, that is alpha p actually corresponds to the PNP transistors, upper one transistors plus ICB1, and similarly you can write this equation from the KCL, you can boil down the same equation which you have, this is in case of the thyristors. So, you can see that this corresponds to alpha 2 and this corresponds to alpha 1, same as here it is been represented by alpha n and alpha p, upper transistors as alpha as transistor 1 and this transistors as transistors 2. So, gate turn on operation is same as of the conventional thyristors. So, whole current will flow, electron current will flow, ultimately this is the direction of the current, and ultimately when alpha 1 plus alpha 2 equal to 1, then the current, anode current basically goes to the conduction mode. And what about actually turn off? Once turn off takes place, you have to inject negative gate current, and thus what happen, actually this transistor required to be in a cut off stage, cut off mode, and for this reason we inject the trap charges and we have to take the base into the cut off mode by applying the negative gate current, and the structures or the leakage current will be flowing only through the PNP transistors, and this portion will be blocked, and thus this is the turn off operation of the GTO. So, steady state operation of the GTO, it is something almost same for the thyristor. The latching current of the GTO is considerably higher than the thyristors of the similar rating. So, due to this structure, actually you require to take this value little larger, then only actually you can put up the gate, otherwise you require to put gate. Forward leakage current is considerably also higher, so that you require to take out the trap charges from that region. In fact, the gate current is not sufficient to turn off GTO, it operates as a high voltage low gain transistor and with a considerable anode current. So, for this we require to do something. So, this is the IL value will be higher than the corresponding rating of the normal thyristors. It should be noted that GTO can block rated forward voltage when gate current is negatively biased with respect to the cathode during the forward blocking state. So, you require to dissipate some amount of the energy to achieve also its blocking stage. At least a low value of resistance must be connected across the gate and cathode terminal. Increasing the value of the resistance will reduce the forward blocking voltage of the issue. This is very important point. So, while you have a forward blocking mode and you require to put little amount of the negative gate current to keep it in actively in forward blocking mode. So, this is something you require to design for it. We shall discuss the gate driver circuit of all the entities starting from thyristors, GTO, MOSFETs and IGBT. These are the 4 major components we generally use in the power electronics. IGCT and other components are now venturing, and the age is yet to come for a normal application because of the high costs, and the technological upgradation still continues. So, all those 4 gate driver circuits will be designed, and we will see that what require what actually fit to do associate what kind of performance. Now, the zone between the minimum and the max curve reflects the parameter variation during the individual GTO. So, it is not that you have a single curve. So, ultimately depending on the IG, the value of mean and max can be changed. This characteristics valid for the DC as well as the low frequency gate current. They do not give a correct voltage when GTO is turned on with high DIDT. So, you require to actually take care of the high DIDT issue in the gate current, and for this reason we require to put a small inductor into the circuit of the gate devices to block it. So, this is a new features that require from the thyristor, and this Vg in this case of the GTO much higher than the SCS of the same rating. And based on the applications or the operations, we can classify as symmetrical operation and asymmetrical operation. That means when let us say AC application, it blocks same forward, it may require to block same if it is triggered let us say alpha more than 90 degree. So, what happen it will be blocking forward peak inversion voltage as well as in a reverse also the same voltage. So, we have discussed in previous slides actually this is the peak repetitive voltage, and asymmetrical GTO VDRM is much greater than VRM, the repetitive voltage, then we say that it is asymmetrical, and mostly this is used for the source inverter with the anti-parallel diode, that is in case of the VSI, voltage source inverter, where VDRM can be as high as 600 volt and reverse recovery voltage can be as low as the same value. And GTO can be used for CSI, that is we shall come across this topology after this, that is called current source inverter, where these two values are almost same, and this is called a symmetrical operation, and their VDRM and ARM you will find that actually it is 600 volt and it is almost close to 600 volt, it is 6500 volt, and so it is used for the CSI. Of course, we have discussed in a graph in a previous class, students are requested to actually see my previous class where I have discussed different terminology while discussing the thyristors. VDRM is the maximum repetitive peak forward offset voltage and maximum repetitive peak reverse voltage. Now, this is dynamic characteristics of the GTO. So, this is the voltage and current across this device. So, once you initiate to turn it on, so since there is a junctional capacitor, it is just like a charging a capacitor. So, it will be actually a ramping on. So, what happened due to that? So, voltage across this device will gradually fall and it will gradually come to the conduction mode, and once you initiate it till Ig rises its value to 1%, from that point you will see that actually what was the voltage, and voltage that time will be the forward blocking voltage. Then you ramp it on to the maximum value, and by that time you will see that actually there will be a drop in voltage across the thyristors will be around 90%, and current also through this GTO will rise by 10% maybe. So, this time basically it is called the delay time in a turn on. So, thereafter it is called rise time, where basically Ig it still reaches its rating, and voltage across this device falls 90% to 10%, and current also rises to the maximum value to 90%. This time is called actually the rise time. That it will continue, same will happen. Here you initiate basically the change, and here also actually it is a 10% of your Ig, and you see that this Ig and this Ig has a huge difference. Generally this Ig is around 4 times, negative current has to be more than 4 times than the forward triggering current. So, it will continue to rise. For this reason there is a problem of high DIDT, or so it will reach to this value. Till that time it will be off, and still it is actually not grown up the capability, and thereafter there will be a forward blocking stage. Thereafter what happen, current will continue for a huge time, it has got a current trail. So, this is the current trail or the T tail time. So, and you require to continue to give. Once you see that actually this value reaches this actually 90% of the rated current, then you gradually decrease the value of the gate current, but you continue to give current once it reaches the actually current and the rated as prescribed by your leakage current. So, huge minus negative gate current is required to achieve commutation or turning off. For this reason, GTO is quite slow device than the IGBT. So, let us just go through the one of the data sheets of the GTO for better understanding of its phenomena. So, VGK it is actually around 2 volt. So, there is one of voltage difference required. So, T junctional voltage can go as high as 125 degrees centigrade. Vd should be actually 80% of the VDRM, and VDRM should be actually more than the VDM, and this thing rate of change of gate current should be around 20. You have seen that is around in the range of 1 ampere per microsecond. It required to be little higher, that is around 20 ampere per microsecond, and CS equal to 1 microfarad. Double side cooled single phase for 50 hertz, 180 degree sine wave application, and since that TP is basically of 2, and for DIDT is basically for this device as high as 1000 ampere per microsecond. So, let us see. So, VDRM, so it should be around 2500. A non peak repetitive voltage will be more than that. So, it is 2600. Repetitive peak reverse voltage, it is actually 100 to 2000. So, it can be used symmetrical as well as asymmetrical. Non repetitive peak reverse voltage, it is 100 to 2000. So, what is important, this is the snubber part that is comes into the protections. So, we shall discuss this zone. Mostly T off permission turn off time, it is basically quite high, that is basically 90 microsecond. So, generally switching frequency should be if you make it around 100 microsecond, if it is reciprocal it will be a 110 kilohertz. So, at least this turn off time should be around 5 to 10% of the total timing. So, for this reason this device is required to operate below 1 kilohertz, and possible turn on time is 20 microsecond. And what else? So, this thing is quite critical DVDT. So, it has to be actually within 1000, and latching current, it is quite high. Latching current required to be 5 ampere. Consider that there actually it is something like in a milliampere region in case of the actually same rating thyristors. Holding current will be also same. Here there is no difference between the latching current and holding current. Holding current generally less in case of the thyristor, but in GTO generally latching current and holding current both are made same. So, they are at a peak offset current, it is 30 ampere. So, thereafter you have to understand the gate triggering voltage once it is triggered. So, these are the typical values with that actually 25 volt and an RL considered to be 25 milliohm, and gate triggering current is required to be generally a 1.5 or 0.5 ampere, and this is for this actually junction temperature. Now, delay time. So, delay time of there is a 2 delay time. So, this is quite important. Delay time will be actually 1.5. Please recall the graph what we have shown. So, this is basically TD on. So, that is required to be 1.5 turn on time, that is actually fall of the voltage across the thyristor across the device 90% to 10%, that is 3.5, fall time is 0.8. Turn off time, you see that actually it is quite high. This is what is important here, the trailing time. Tail time is as high as 50 microsecond or 75 microsecond, and turn off gate charges basically you require, this is the amount of the charge it has been trapped, you have to take it out. So, this tail time is quite large, and due to that you require actually this device to higher turn off time. So, this is the weight is also little bulky than the thyristor. So, what is the difference between the thyristors and the GTO? Problem of thyristor that it is difficult to put off except you have a line commutation in AC, it is naturally commutated. Otherwise, you have to find some means to actually take the current through the thyristor below its holding current to put off, either by having an LC oscillations, so that you put actually it may require auxiliary thyristor. You may require a bypass path, so that current actually bypassed and you trigger another thyristors. There is a different kind of commutation technique or the turning off the thyristors. What you require essentially either extra thyristor or you require an LC circuit, so that you can underdamped LC circuit, so that you can have a oscillation. But commutation failure may occur in the high current within the small interval of time where you are applying the negative voltage. If thyristor current does not goes below the holding current, so its forward blocking capability will not be there. But GTO has an advantage that you can put off that where you require. So, that is the one of the biggest advantage of it. I can take an example, in case of the thyristor, let us say for the rectifier operation, you can turn it on here and you will automatically turn it off here depending on the kind of load you are having, if you have a resistive load you are having. So, essentially what is your fundamental current? That will be lagging, because this is the displacement power factor comes into the picture and current will be lagging like this. But in case of the GTO you have an advantage. So, here you may trigger it on here, and you can also trigger off here, and ultimately you get this kind of voltage. And what happens then? The fundamental current will be in the same. So, you can have a unity power factor or leading or lagging, you can chop it here, and this way you can control the power factor of the system. This is one of the biggest advantage of it. And in between you can go for the, if you require, we will discuss about the selective harmonic elimination and all those things that can be achieved here. But in case of the thyristor, you can only control alpha, thus you can only control only one angle. So, thus you can eliminate only one harmonic, that will come later. So, let us go back. What are the difference of the GTO and the thyristor? GTO is essentially, this is the one of the major feature, otherwise this is inferior device considered to the thyristors in all the respects. GTO is fully controlled, you can turn it off as turn it on at the will of the user, but it is a semi controlled device. When on state drop in case of the thyristors of the same rating will be around 2 to 3 times higher. So, for this on state drop is around 3 to 4 volt, but you will be having this around 1.5 to 2 volt. It is because of, if you go back, so we have seen that there is a negative blocking state. So, here this buffer layer is there for the higher forward blocking voltage. So, for this reason, to incorporate it, you will also incorporate higher losses. Higher holding and latching current, we have seen that it is around 10 times higher than the actually the normal corresponding rating of the thyristor. So, lower holding and the latching current. So, generally it has same forward and the reverse blocking voltage, and you will have a symmetrical operation. But here you can have a asymmetric operation also, all the symmetric operation, and you can control and modify it according to the gate current. So, you can apply little bit of negative gate current to put it off to increase its forward blocking capability. These are the few flexibilities it provides. And typically it has high DVDT. So, it will have a 1000 volt per microsecond, but it will have a lower DVDT. For this it required to be designed properly for DVDT and DIDT protections. And turn off gain is actually 6 to 15. So, this is a wide range of variation how fast you want to turn off. So, you could require to put a more gate current. If you give a small gate current, it will current trail will be much larger and you require to take much longer time to put it off. So, since there is no provision by gate turn off, so that is not there in case of the GTO. And as I have shown you that actually current trail is of a typical GTO is in the range of the 50 microsecond. So, for this reason we are restricted to operate it in the range of 1 to 2 kilohertz. So, we have maximum you can take it to the 4 kilohertz, but it is quite difficult to actually operate, and therefore, this is actually buck will be pass on basically on this actually the turn off of the gate current. So, you require a gate current to turn off these devices, and this is typically operated in a 50 hertz supply and mostly in a converter operation where you have SCS is operated for the, and the name suggests is rectification, as you can understood, that is applicable for the natural commutations, and it will commute this actually at it operate in a normal power frequency of 50 and 60 hertz. So, these are the differences of the GTO, and we shall see that where if possible definitely the takeaway from this class is if possible use thyristor, if possible use SCR, but if you cannot you require to turn off In between, for many reasons, for the selective harmonic elimination, for improving the power factor or any other region, then we require to GTO. So, thank you for your attention. We shall start with another device in next class.